spend a bit of time talking about dynamics. We're talking about statics. And when we say statics, you know, it's just reading at a given time. Dynamics, we're concerned about what's going on, okay, with the airplane over time. We define static stability as what?
Instantaneous.
Essentially, the tendency to return, right? Like I say, that's a foot stomper, okay? The tendency to return the trim, the initial tendency, okay? So it happens, you know, quick, sort of instantaneous. That's static stability. Dynamic stability is what happens over time. And we said there were how many cases of dynamic stability? Or how many, you know, how many different dynamic stability kinds of things can you have?
Three.
Double that.
6.
Okay, 6. Let's think about it. If you have an airplane that you displace from trim and then let it go, and it just diverges that way or that way, it just diverges. That's one case, right? And in that case, it has both negative dynamic stability and negative static stability because it has no tendency to return to trim. Right? That was the case of the bowl on the table, and you set the ball on the top of, you know, the bowl upside down, it rolls off and goes away. Okay, that's one case. Okay, let's look at another case. In this case, we have positive static stability and we displace it and we just let go and it goes right back to trim. Doesn't oscillate or do any of that, just goes right back to trim. Positive static and dynamic in that case, right? Okay, then we'll use this airplane here. So, then we take it and we displace it, and it's real happy there. Over time, it just stays wherever we displaced it to. In this case, it has neutral dynamic and neutral static, right? So there's 3 cases that we can have with an airplane. Now, there's 3 more. All of the 3 more have positive static stability. Initial tendency is to return to trim. And what happens is they are oscillatory cases. All 3 of those are oscillatory. So we displace it, let's say we displace it 10 knots from the trim speed and we let go and it starts back to trim, goes through trim and then, pulls back up and goes through trim again, and it does that several times before it damps out. Back at trim speed. There we have positive static because it had the tendency to return to trim, right? And positive dynamic because it eventually did. Okay, then we have the next case. In this case, we have neutral dynamic, positive static. We displace it from trim. It tries to return to trim, but it goes right on through and an equal on the other side, and it sits there and it'll do that forever. Positive static, neutral dynamic. Generally, you will see that in climb for some airplanes. Okay? Although, it may exhibit itself in other cases, but where I've seen it with airplanes, a Cessna 310, for instance, if you displace a Cessna 310 from trim and climb, it will sit there and oscillate all day, as long as you continue to climb. Yes, sir?
Does neutral dynamic stability, does that also include varying amplitudes, but it keeps returning?
No, the amplitude stays the same.
Totally the same, the amplitude doesn't oscillate?
Yeah, the amplitude stays the same, okay? So we've got neutral dynamic, positive static because of the tendency to return. The third case of this is positive static, still tends to return, but each time the amplitude gets bigger and bigger. Negative dynamic. It will not come back to trim, okay? It just gets bigger and bigger, although it tries. That same Cessna 310 in the power approach configuration is that. Generally, when you do this in a 310, you don't want to let it go more than about 2 cycles, because you're either going to overspeed the flaps or you're going to stall, because it just gets bigger and bigger. Okay, so 6 cases, 6 possibilities for dynamic stability. Essentially, it's a study of how one equilibrium flight condition is changed to another, or how the airplane responds to a disturbance in pitch with time. Okay? It's good that the longitudinal dynamic stability motion doesn't couple with other motions as a rule. You can almost, in longitudinal cases, you can almost consider as the airplane is 2-dimensional. Now, when later in the class, we're going to both talk about and look at lateral directional stability. That's a different ballgame, okay? But longitudinal, airplane's pretty much 2-dimensional. You can look at it from the side and, see all of these things. Principal variables in longitudinal dynamic are the pitch attitude, the angle of attack, the airspeed, and the elevator deflection in the case of stick free. Okay, so when we do this, when we do longitudinal stability, and we'll try to combine that when we do static, we'll do, say, the climb case static, and then we'll turn this thing on and let it run, and we'll record the dynamics for climb. And then we'll turn around and we'll do the statics for power approach. And when we get through with the statics, we'll turn this guy on and record the dynamics in power approach, okay? And so these will be important parameters. Unfortunately, we don't have angle of attack in this box. I think you could probably, deduce what it is, but we don't have it directly recorded. But we do record airspeed, we record pitch attitude, and we record elevator deflection. So you'll have all of those data from the data. And you'll see the oscillation. Now, fortunately, or maybe unfortunately, depending on your outlook, the Cherokee 6 has oscillatory longitudinal dynamics, okay? It's a nice stable airplane. It has a stabilizer with a leading geared tab, and we're going to talk more about that, and I'll show you those things when we go to the airplane. And that nice leading geared tab tends to drive dynamics back. So it'll oscillate a few times, but it'll come back to trim in all cases. Not every airplane will, and particularly airplanes that don't have leading geared tabs, you see some of these events. But we'll be able to plot this up. You'll be able to take it off the lunchbox and plot it up and see how the airplane performs and how quickly it subsides. That's one of the things we'll look at in dynamics. How quickly does it subside? Anyway, those are the variables we look at. Now, one of the things you're going to see, if you could see angle of attack, is that during this oscillation, angle of attack doesn't change. Whoa! Now, the guys for 27 years, I taught at the University of Tennessee, Space Institute in Tullahoma, Tennessee. Well, right next door there is the Air Force Arnold Center. It is the world's biggest wind tunnel complex. Okay, they have wind tunnels there. Will just water your eyes as to what they will do. They've got test sections bigger than this room. Okay, that are capable of sustained Mach 2.5. Okay, you know, if we get a 2.5 tunnel in most universities, the thing's about that big, right? That's the test section. And so, but they have the capability there to run a continuous sustained Mach 2.5. They only do it at night because it requires all the excess power that the TVA electrical system can generate. So it only runs between midnight and 6 o'clock in the morning. But they have several other tunnels there that do all that. But the wind tunnel guys used to come and take my flight test courses. To make a long story short, they would come and take it, and in a wind tunnel, angle of attack and pitch attitude are one and the same. Okay? They're locked together in a wind tunnel. Out in free flight, angle of attack can stay constant while the pitch attitude's doing some really strange stuff. Okay? Because what's going on with this oscillation is that the airspeed's changing. And so the relative wind during these dynamics is generally right at the same place on the airplane. That makes sense? So that's what's going on. That's why if you see angle of attack start to change, you can almost guarantee that the dynamics are unstable. Okay? On that Saratoga, if we could measure angle of attack, we'd see that, you'd get awful bored, whoever was recording angle of attack, because you could almost write down whatever it was from the start and forget about it. So it's worth talking about that. 3 modes of longitudinal motion are long period motion or phugoid. Now, you say, where is that? Well, of course, that's a Greek letter. It was a Greek word, and it came from a fellow back in the mid-1800s by the name of Lanchester. He was an Englishman who actually did a lot of experiments with both models and actually built a full-scale airplane, which flew with his coachman aboard. I understand that after the flight, the coachman quit. Said, I don't want to do this anymore. But Lanchester termed this term phugoid. Now, what he did was he made a mistake. Phugoid means to flee. Of course, that's what his coachman did. But he was looking for another Greek letter, or Greek word that's spelled similar that means oscillation. Okay. But anyway, phugoid stuck for reasons unknown. And we call it the phugoid. And what we'll look at in the class, well, we'll look at both of these, but the one that you'll record will be the phugoid, the long period dynamic motion. Okay? Another one is the short period. On most general aviation airplanes like we'll fly here, the short period is very heavily damped. Okay? I mean, you do a doublet input, generally is the way you try to excite it. And you may, at the most, see one overshoot after you let go of the control. Very heavily damped. However, take an airplane like a jet fighter, it's got a lot of mass in the fuselage, not so heavily damped. For instance, the U.S. Air Force, well, first the U.S. Navy built the F-4. Okay? And the Navy intended for the F-4 to be an up and away, you know, go out and shoot at the Russian bomber kind of airplane. Okay, and you know this is Cold War stuff, you know, in the past. But anyway, that was what the design was, to take off from the aircraft carrier, go out and intercept the bomber coming in to blow up the aircraft carrier. Fine, nobody had any problem with the short period dynamics, and the Air Force bought the airplane. And the Air Force intended to use it for low level. Well, all of a sudden, people were sticking airplanes in the ground. Because the short period motion, which is about at the human reaction time, was not so good on the F-4. And particularly the pilot would tend to get in the loop because its frequency was right at his. And so they did a big investigation as to what's going on. Nobody, prior to that time, nobody worried much about the short period. Okay? Because it was always heavily damped. Well, on those airplanes, it wasn't so heavily damped. And so, you know what the solution was? And I understand it's in the pilot's flight manual for the F-4. The solution was, let go. Don't hold the control. When this thing starts this, you're feeding it because your reaction time and it are the same. So this is the short period motion. It is the most dangerous one. The FAA, in the regulations, worries about the short period. They have no requirements whatsoever for the long period. That's how the Cessna 310 got approved with the very bad long period that it has, okay? Is that there's no requirement in the FAR. You can go look in Part 23. You'll find it. You won't find anything talking about the long period. Short period, on the other hand, is there. Okay. The long period are phugoids used by the pilot to make airspeed changes. The short period, you know, the initial maneuvering task, we talked early on, we talked about, we said that static stability was primarily concerned with the non-maneuvering task. Well, when we start maneuvering the airplane, we start turning, the initial inputs are pitch and angle of attack changes without a change in airspeed. Okay, the non-maneuvering task, we see a change in airspeed. In the maneuvering task, we do that without a change in airspeed, at least initially. And that motion is associated with the short period. That's where the short period shows up. And the uncommanded elevator oscillations, which result in airplane angle of attack change, describe the elevator short period. There's the airplane, overall airplane short period, which is most folks concerned about. But my first flight test job at Beach, we had an airplane called the Model 99. And the Model 99 was a very early commuter airliner. Okay, some of you may have seen them, may have even flown on it. But when they built the tail for the Model 99, the tail was built not in Wichita, it was built out in Liberal, Kansas. Now, when I worked at Beach, we used to say that liberal was out near the edge of the earth, because when you go out there, you think you're not far from the edge of the earth, okay? But anyway, their tooling in liberal was not too good, and what caused the problem with this airplane was that it had, you don't want to design an airplane with curved controlled surfaces. The 99's elevators were curved. And the trouble is, when you build them, one side will get bigger than the other, okay? And what would happen, particularly if the leading edge was contaminated with ice, or actually the way we were testing, we'd inflate the de-ice boots on the horizontal tape. And when you leveled off, this thing would sit there and do about a 0.3 of a G oscillation for about 20 or 30 oscillations. You know, you're sitting there in your seat going like this, and of course that scared airline passengers to death, you know. So we went about fixing it, but it was an elevator short period. It was driving the airplane, and what we did to solve it was we put 1/4-inch high wedges, one on the upper surface of the tail and the other one on the bottom surface of the tail of the elevator. And if you ever see a 99, or actually a King Air 100, it has the same tail as a 99. If you see those airplanes at a, go around and look at the tail, and you'll see the little wedges that we put on there to fix that problem. But anyway, that's the elevator short period. So there's two kinds of short period for airplanes that have reversible control systems. Irreversible system, you know, that system holds that elevator so it can't flop up and down like it can with a reversible. Okay, I think it's lunchtime. We'll stop here and we'll pick up here when we come back from lunch. When we look at dynamics, particularly the longitudinal stuff, looking at simpler mechanical systems are useful. And of course, one such system is the spring mass damper, which I have drawn here. We have some mass, and we'll assume the wheels don't have any friction. We know that's not true. We've got the spring here, and this is the damper. And we exert some force on this, and it's going to sit there and oscillate. If we neglect the friction on the wheels, the differential equation which describes that system, we can come up with the first one. And if we divide by the mass, we can end up with the second equation. And these are non-homogeneous second-order differential equations with constant coefficients. And the coefficients are determined from the physical characteristics of the system described by the math model, i.e. mass, damping coefficient, and the spring constant. And the force, F sub parentheses T, is the forcing function. And if that equals 0, then the response is referred to as the free response. And the general solution of the non-homogeneous differential equation is the sum of the homogeneous and particular solutions. And a homogeneous solution is the solution when F sub, or parentheses T, equals 0. And a particular solution is a solution when substituted into the left-hand side of the equation and yields the right-hand side of the equation. Well, in the following discussion, we'll evaluate the free response, or what's called the homogeneous equation. And the solution of that equation is x, which is the distance, right? Times t times a coefficient times e raised to the s of t. power. And if we substitute that into the left-hand side of the equation, we end up with S squared, a plus operator, times A e to the st, and so forth. And if we divide through by A to raised to the e to the s raised st power, we have S squared plus C over m times S plus K over m is equal to 0. And we call that the characteristic equation. And the roots of that equation are called the eigenvalues of the system. And they are the Laplace operator S is equal to the damping over 2 times the mass plus 1/2 or 1 over 2 times the mass times the square root of the damping squared plus 4 times the mass times the constant K. And the form of the solution of the homogeneous equation will depend on the damping with 3 possibilities. Okay, C squared greater than 4 times the mass times that constant. We have distinct real roots, i.e. over damping. Okay. The second case is C squared less than 4mk, and we have complex conjugate roots under damping. And then C squared is equal to 4mk, a real double root called critical damping. Now, we end up plotting those. We can plot those on the complex plane. And so if we draw the complex plane, and we have, this is the real axis, we'll just call it real. And this is the imaginary axis, call it I omega. And if we have a root that's on this side, we know that that's a negative real root. Am I right? Yeah, okay. Been a while since I did this, so you'll have to. What we have with airplanes generally, and longitudinal airplane motion in the positive, I say this is the, as far as stability goes, the negative side. This is, as we go this way, the damping gets heavier, okay? And if it's on the axis, we know that it's not oscillatory. Okay, it doesn't oscillate. If we have an imaginary component, let's say we have a pair of roots like that, we know that these roots are damp since it's on the left side of the axis, and we know that it's oscillatory due to the fact that there's an imaginary component. Okay? The phugoid motion, the roots end up being very close to the axis. Sometimes they're on this side, undamped, okay? You know, like I said, that Cessna 310 had an undamped phugoid motion. It kept getting bigger and bigger. Those roots fell over here. Normally, Saratoga is probably over here someplace, but generally they're pretty close to the imaginary axis. Short period, we said it's heavily damp, but it's oscillatory. So those roots are going to fall somewhere like that, okay? So we can use this imaginary plane as a way of giving us an idea of what's going on. And if we make changes to the airplane, we can calculate where these roots are going to go and get some idea of whether our dynamics are going to be stable or unstable. The ratio formed by the actual damping and the critical damping is called the damping ratio. And of course, the critical damping is 2 times the square root of K times the mass, or 2m times square root of K over the mass. And for a system where the damper is removed and the damping is 0, the system will have an undamped oscillation. Okay, so the Cessna 310 in climb had an undamped oscillation. It would just sit there and continue to go. And so, according to that then, it didn't have any damping, it had 0 damping. Probably not something that we want. And the frequency of this undamped oscillation is called the undamped natural frequency. And by substituting the undamped natural frequency and the damping ratio into the second equation that we had up there, okay, undamped natural frequency, damping ratio, undamped natural frequency, and S is the Laplace operator. And for an aircraft, the previous equation is a form of the characteristic equation for the control transfer function. And the transfer function describes how the airplane responds to a control input or some external excitation like hitting a gust. Okay, the airplane hits a gust or what have you, it's going to respond. And the transfer function tells us how that would be. And the transfer function is obtained by applying Kramer's rule of determinants to the coefficient matrix obtained from the equations of motion. Here's where we start. Dynamics is where we deal with the equations of motion. And the longitudinal determinant from which the characteristics equation is derived. I just quoted the textbook there because that determinant is pretty big. And before leaving the simplified characteristics equation, it's worth evaluating what its roots mean. We plot the roots of the characteristic equation in the complex plane, which we did over there. We can learn about the motion of the system. If the roots fall on the real axis, we said we know the system is heavily damped and described by a first order response. Now we talked about the 3 cases where the airplane either immediately displaced from trim, went right back to trim, okay, or if displaced, it just went away. Well, that's going to be a real root on either one side of the imaginary axis or the other. And such motion has a time function of e to the raised to the at, which is a Laplace transform. And this is where you can use Laplace transform. So 1 over the Laplace operator minus a, and whose characteristic equation is just s minus a is equal to 0. And the root is in the left half plane, negative real part. The motion is stable. If it's in the right half plane, which we talked about, it's unstable or divergent. And secondly, if the root has an imaginary component, the motion is oscillatory with the distance the root is from the real axis, depending on what frequency it is. So if the roots are in here real close like that, you know that it's it's going to damp eventually, but it's going to be a very slow oscillation. If they're up here, like these short period roots, we know that, you know, the short period frequency is quite high. And as a result, that gets back into about how we can respond, okay, as people. You know, we have a response frequency. And the interesting thing about that is we're all a little different. We all already knew that, that we're all a little different, but our response time is a little different. And that's why we were talking about the F4 before lunch. A lot of pilots didn't have any problem with it. Only certain pilots would get this short period oscillation. But their frequencies were such that they would excite the thing, and other pilots wouldn't see it. And that's why in dynamics sometimes it's worthwhile if you have you know, you pay attention to the one guy you think is you know, maybe not such a good pilot. It's one of the problems with pilots, okay? We all think we're the greatest around. Okay, yeah, I'll be real honest. We all think we're super. Trouble is, we're all not. and so, you know, some of us respond differently to that. And so as a result, a lot of times, one guy will have a problem, nobody else will, and so everybody generally will just kind of ignore it. Yeah, oh, Joe, you know, we know he doesn't, you know, he's a little slow. He doesn't, he's not a very good pilot. That's what we're really thinking. Turns out he may be a great pilot. His response time is such that it gets into the loop with the airplane. So that's one of the reasons for using all this mathematics, which I always have to relearn about every time I teach it. Okay, the root has imaginary component. We said the motion is oscillatory, and the farther they are from the real axis, and the distances from the real axis is represented by the damp frequency. Oh, let's see. Okay, here is this plot. All right, and let's say we've got a couple of roots right here. Well, this length of this line is the natural frequency. How far it is from the x-axis is the damp frequency. Now, when we go out to test this, what are we going to get? We're not going to get the natural frequency to start with, are we? We're going to get the damp frequency because the airplane has some damping. And so here's the damp frequency, and this is you know, a real component of that. And this angle, theta, you know, tells us where this root is located. And these lines that are on here show levels of natural frequency, and these various angles show damping. Well, the damping ratio is defined by the cosine of that angle that we had. Oop, went the wrong way. This angle, cosine of this angle. So that's the damping ratio, is defined by that. The period of the motion is defined by 2 pi over the damped frequency. So we go out and let's say we do a phugoid. And we can determine what the frequency is, right? We can just count the peaks. If we want to do that. We can determine how many cycles it makes, or hertz. I've never understood this, but the electrical guys some years ago, actually this came about within my lifetime. In fact, I was in the Air Force at the time it happened. And prior to that, we'd call them cycles per second. And then they just, somebody decided that we would name this cycles per second after this guy by the name of Hertz. I always thought, prior to that, I always thought Hertz was a rental car. Okay. But now it's named, so many cycles per, or so many Hertz. Well, to me, cycles per second makes a hell of a lot more sense. But anyway. But we can get that. We can get the damp frequency, and that's what we're dealing with when we actually see the oscillation, right? So the period is 2 pi over the damp frequency, so we can solve for that. And we can plot the thing up. Time to double amplitude or half amplitude is essentially 0.0693 over the real root, and number of cycles to double or half amplitude in most cases, and this is kind of a rule of thumb, the damp frequency over the real root, and so we can get this in like that. We assume that the angle of attack remains constant for the phugoid minor, and we said the phugoid ends up plotting up, very close here. It doesn't oscillate very fast, so these roots are in close, and they may, they can move over here, which would mean that they would be unstable. The oscillation would get bigger and bigger over time. The angle of attack remains constant and the pitching moment characteristics cancel one another. Then the longitudinal determinant reduces to the phugoid minor. And here is the phugoid minor, where we have the Laplace operator times the drag in the x direction, okay, times the Laplace operator, and times acceleration due to gravity, lift in the x direction, or from the x direction, and velocity in the x direction. And if we evaluate that, the natural frequency ends up being square root of 2 times the acceleration due to gravity times the velocity, and the period is just 1.38 times the velocity. Damping ratio for the phugoid, 1/2, or 1 over the square root of 2 rather. CD over CL, and we can convert that. It comes out about 0.707 times the lift over drag. So what does that tell us? What it tells us is that the lift and the drag of the airplane is going to affect the long period motion. Because what's going on as the airplane is going away from trim, nose up, okay, drag, what's happening to the drag? Drag's going down as the airspeed decreases, right? And when it starts back down, drag increases. So this thing is this, if you fly beside an airplane doing a phugoid, it looks like it's on a spring. Sitting out there, it goes up and down. If you match airspeeds with an airplane doing a phugoid, you watch him and he does this. You can kind of see the spring mass damper thing going on, okay, and that's why it ends up being used. What we're showing there, those are just really only approximate values of the phugoid parameters, good rule of thumb kinds of things. And we flight test guys tend to like to use that. We're not big mathematicians as a rule, so we do that. Okay. Again, in my book, if you look at those pages, you'll find a similar for the short period. Short period equation is a bit more complex, and it's characterized by a change in pitch without an angle of attack change, or for that matter, an airspeed change. So the short period occurs very quickly. The airplane doesn't have time to respond in airspeed when you have a short period motion. You will see an angle of attack change. He said we didn't see an angle of attack change in the phugoid. With the short period, you're going to see an angle of attack change. And the frequency, as we said here, is pretty high since this is a long way from the real axis, and ranges between 1/2 and 5 seconds. 5 seconds is pretty long, and generally the airplanes that have the long one are airplanes that have a lot of mass in the fuselage, i.e. jet fighters, okay? They're the ones that are most likely to show a problem with the short period. As with the Saratoga, I'll do some doublets and to look at the short period, but you won't see much response. We did some yesterday with the lunchbox. I don't know, we had more than about one overshoot, right? It was about what it turned out. So generally light planes are very heavily damaged. Fuselage-loaded airplanes, I already mentioned that, can become a problem since frequency is near those human. The pilot gets in the control